Hello AP Physics students, this is Mr. Everly again. This is a supplementary video just to explain in video form Ampere's law and how it applies to a single wire and then how it applies to a solenoid. Now Ampere's law is very similar to Gauss's law, except, don't panic, it's much simpler. So by the way, all of this is explained in your textbook as well. I would strongly encourage you to read sections 29-4 through 29-6 in the book, and basically section 4 through the end of the chapter. The more you read about this, the more perspectives you get, the better you're going to understand this. Now, again, the magnetic field around a current carrying wire. Imagine we've got some wires that are carrying currents. Let's say this one is downward. We've got another wire over here that's sending a current upward, and another one over here that's sending a current upward. Let's say from above, these wires are configured as shown. So here's our downward one, current going down into the page, current coming up out of the page, current coming up out of the page, these two guys. Basically what Ampere said was, imagine we put a loop around the wire. Now, instead of a Gaussian surface that we're going to enclose something in, we're going to take a mathematical loop and say put it around these two wires. Okay, maybe from above it will look like this. Okay, then we're going to integrate around the loop. Okay, so there's a definite direction of integration. As we integrate around the loop, we're going to look at the current enclosed inside the loop. Any current outside the loop, its magnetic field will cancel out. Inside the loop, we're going to find that the integral, the closed integral around the loop, B dot ds is equal to mu naught, that's that permeability constant for magnetic field lines, times the enclosed current. Now as we integrate around, as we normally do, we break this thing up into lots of pieces. So imagine we've got one little ds here. Let's say the magnetic field is in this direction at this point. Theta is the angle between the magnetic field direction and the direction of ds. If we integrate around this way, one of these currents is going to be clockwise. I beg your pardon. One of these currents is going to be positive and one will be negative. And as you integrate around in this direction, use the right-hand rule, and your thumb will point in the direction of positive current. So as we add these up, if we call this current 1, current 2, and current 3, current 3 is outside the loop. We don't even have to worry about him. Current 2 will be a positive current. Current 1 will be a negative current if we integrate around in the clockwise direction. Okay, so this is the magnetic field. This is ds, a tiny segment as we go around the loop. Mu naught is the magnetic permeability constant. I here, I enclosed, is the sum of currents that are passing through the loop. Okay? So, kind of a weird thing. Interesting. Let's apply it to a single wire. Once again, just like with Gauss's law, we're going to look for situations with symmetry so that we don't have to worry about errant magnetic fields from other wires and so on. We're going to look for areas of symmetry. So the simplest situation would be a single wire. Okay, we've got a current this way. If we look at it from above, the wire has a current coming up out of the page. If we put an Amperian loop around this wire, looks something like this. We're going to integrate around counterclockwise. Okay, that's supposed to be a circle. I'd like to know what is the magnetic field right there a certain distance r away from my wire. So right there, what is the magnetic field? Okay, once again, because of the nature of the wire, the magnetic field around the wire, if I grab hold of the wire with my thumb in the direction of the current, I know that right here, the magnetic field is tangent to the circle. Okay, ds is also in this direction, so they're parallel to each other. We've got a dot product here when we write Ampere's law. B dot ds equal to mu naught I enclosed. Okay, if B, the magnitude of B, is the same everywhere here, again, we're going to use the symmetry that B is the same everywhere on this loop, then I can pull B out of the integral. The current enclosed in my loop is just the current in the wire, which I called I. The integral ds then, if only ds is in the integral, when I add up all these ds's, all I get is the circumference of this circle. So it's 2 pi r. So if I solve for B, we get our familiar equation for the magnetic field around a current carrying wire. So Ampere's law works for a single wire. At least it agrees with B.O. Savart. We can also use Ampere's law to find out what is the magnetic field within the wire. So if I have a wire that is pretty thick here, and we've got a uniform current density going through it, let's call the current passing through this entire wire I total. Question could be, what is the magnetic field? If we look at this wire from above, the current is coming out of the page. What is the magnetic field some distance from the center? So I'm going to call this distance from the center r. We'll call the entire radius of the wire r, big R, and we're going to say, okay, when we're this distance from the center of the wire, what's the magnetic field within the wire? Okay, and again, imagine all the currents coming up out of the page. In order to do this, I'm going to imagine an Amperian loop within the wire. Okay, has a constant radius, same distance from the center of the wire everywhere, and we're going to write Ampere's law. Okay, and notice that the current enclosed in my Amperian loop is not the entire current through the wire. It's going to be a piece of it. Okay, so how much current is going through the wire? Well, we could say that the current enclosed in my Amperian loop is to the total current as the area enclosed by my Amperian loop, call it pi r squared, is to the area of the whole thing, pi big R squared. Okay, so if I solve for I enclosed, let the pi's cancel out, I get I total times little r squared over big R squared. Once again, the magnetic field everywhere on my dotted line is going to be the same, so I can pull it out of the integral, leaving me with the integral of ds, which is the circumference of this circle. So again, I've got b times 2 pi r is equal to mu naught times the enclosed current, which is I total little r squared over big R squared. So letting an r cancel out here and solving for b, I've got b equals mu naught I total times little r all over 2 pi big R squared. So in other words, the magnetic field, as you go from the center of the wire outward, increases with little r. Mu naught, the total current, 2 pi, and big R are all constants. So B is a linear function of the distance from the center of the wire. The magnetic field grows until we get to the outside, and then it'll get smaller as we move out. All right, so outside of the wire, this equation rules. Inside of the wire, this equation rules.